Good evening. Wherever you are right now, however the day behind you happened to unfold, you can let it begin to settle. There is nothing left for you to do tonight. No problem waiting that cannot wait a little longer. So find a position that feels easy, let your shoulders soften, and allow your breathing to slow into its own quiet rhythm. Tonight we are going to travel somewhere very far away, and we are going to do it slowly, gently, with no hurry at all. We are going to look up at a single point of light in the southern sky and ask a simple question about it. And that question will carry us across an ocean of darkness, so vast that the mind can only ever hold a small corner of it at one time. That is fine. You do not need to hold all of it. You only need to listen and let the words drift past like distant stars sliding slowly across a window. The place we are traveling toward is the nearest star to our own sun. Its name, when you say it softly, sounds almost like a lullaby in an old language. Proxima Centauri. The word Proxima comes from Latin, and it simply means nearest. It is the closest star to everything we have ever known, the closest to every ship we have ever launched into the dark, the closest to every person who has ever breathed on this planet, and the closest to every civilization that has ever risen, flourished for a while, and then quietly faded back into the soil of time. And yet, even being the nearest of all the stars, it sits at a distance that is almost impossible to feel, 4.25 light years away. Tonight we will sit with that number for a long time, turning it over slowly, the way you might turn a smooth stone in your hand by a fire, until it begins to reveal what it really means. Most people, when they hear that a star is only a little over 4 light years away, file it away as a comfortable fact. It sounds close. It sounds, somehow, reachable. With enough patience and enough cleverness, surely we could build a ship to cross that gap. And for a long time, that gentle assumption was where the thought ended. But there is something deeper hidden inside that distance, something that does not simply test the limits of our machines. It presses against the limits of the universe itself. By the time this long night is over, you may come to feel that the journey to the nearest star is not merely a difficult engineering task waiting to be solved by a future generation. It may be one of the few problems woven so tightly into the fabric of reality that it resists every tool we have ever made, and perhaps every tool we ever could make. There is no alarm in that thought. There is only wonder, and wonder held gently is one of the most peaceful feelings there is. So let us begin where the story itself began, not with rockets or equations, but with a quiet observer looking patiently at the sky. There is a faint red point of light low in the southern heavens, in a constellation called Centaurus, the centaur of old mythology, half man and half horse. You can only see this region from southern latitudes, where the night sky tilts to reveal stars that northern eyes never glimpse. And even there, this particular star is far too dim for the unaided eye to notice. It is a small, cool, reddish ember of a sun, so faint that for the whole of human history it went entirely unseen. No ancient sailor steered by it. No early shepherd wove a story around it. No temple was aligned to its rising. For tens of thousands of years, while people gazed up and named the brighter lights and built whole mythologies in the spaces between them, this nearest of all stars simply waited in the dark, unnoticed and unnamed. It remained hidden until the year 1915. A Scottish astronomer named Robert Innes, working at an observatory in Johannesburg in the southern hemisphere, was patiently surveying the heavens when he noticed something unusual about one particular faint red star. It seemed to be drifting across the background of more distant stars more quickly than its neighbors. This slow apparent motion, which astronomers call proper motion, is one of the gentlest clues the sky can offer. Stars that appear to shift their positions relatively quickly tend to be the ones nearest to us. In the same way that a tree at the edge of the road seems to rush past a moving train, while distant mountains barely move at all. Innes followed this clue with care. He measured the tiny shift in the star's position as the Earth traveled around the Sun, a method called parallax, and from that small wobble he calculated its distance. The answer was remarkable. This dim red star was closer to us than any other star yet measured, and so he gave it a name that fit its quiet importance: Proxima, the nearest. It is worth pausing here, just for a moment, to feel the strangeness of that. For all of recorded history, humanity had no idea which star was its closest neighbor. The information simply was not available to us. And then, just over a century ago, in a single careful observation from a southern sky, we learned the name of the door at the very edge of our own little corner of the cosmos. That door is 40 trillion kilometers away. Let us write that number out together slowly with no rush. 40 trillion kilometers, a 4 followed by 13 zeros. It is the kind of number that the mind reads but cannot truly grasp, because we have nothing in everyday life to compare it to. So let us try to build a feeling for it gently, with a simple, almost sleepy thought experiment. Imagine a car traveling along an endless highway at a steady 100 kilometers an hour, never stopping, never slowing day and night, through every season for year after year. To cover the distance to Proxima Centauri at that speed, the car would need to drive for roughly 45 billion years. And here is the part that settles softly over the mind. The entire universe, from its very beginning until this present moment, is only about 13.5 billion years old. You would need more than 3 times the age of the universe itself, driving without pause, simply to reach the nearest star. That is the size of the gap we are speaking of. That is what 40 trillion kilometers feels like when you let it sink in slowly. To understand the distance properly, we need to understand the measuring stick we use for it, which is the light year. A light year is not a measure of time, though its name might suggest otherwise. It is a measure of distance. It is simply the distance that a beam of light travels in the course of one Earth year. And light, as far as we know, is the fastest thing the universe allows. It moves at very nearly 300,000 kilometers every single second. That speed is so great that it almost loses meaning, so let us hold it for a moment in gentler terms. In a single second, a beam of light could circle the entire equator of the Earth about 7.5 times. In just over a second, light crosses the gulf between the Earth and the Moon. In about 8 minutes and 20 seconds, it travels the whole long way from the surface of the Sun to our eyes, a distance of roughly 150 million kilometers. And in the course of one full year, light travels approximately 9.5 trillion kilometers. So when we say that Proxima Centauri is 4.25 light years away, we are saying that even light itself, the swiftest messenger in all of creation, needs more than 4 years to make the crossing. The light that is leaving that small red star tonight, this very evening, will not reach the Earth until sometime in the early part of the next decade, more than 4 years from now. And the reverse is also true, and it is one of the most quietly beautiful facts in all of astronomy. When you look at Proxima Centauri, you are not seeing it as it is. You are seeing it as it was more than 4 years ago, when the light first departed on its long journey toward you. You are looking, in the most literal sense, into the past. This is true of everything in the night sky. The sun you see is the sun of 8 minutes ago. The moon is the moon of a moment past. The stars scattered across the darkness are each a small window into a different distant yesterday, some of them years gone, some of them centuries, some of them so far away that the light reaching your eyes left before the first human being ever walked upon the earth. To gaze up at the night sky is to look out across a great still gallery of moments that have already happened, arriving one by one, each at its own pace. after crossing the patient emptiness between us. And the light of our nearest neighbor has been falling through that emptiness, at the greatest speed the universe permits, for more than 4 years before it ever touches your eye. That, more than any other single thought, is the scale of the problem we are gently exploring tonight. Now let us bring this enormous distance down to the level of our own machines, the fastest things our species has ever built, and see how they measure against it. Humanity has, in fact, already sent objects out toward the spaces between the stars. 2 of them, in particular, launched within weeks of each other in the year 1977. They were named Voyager 1 and Voyager 2, 2 small robotic travelers that set out to explore the outer planets, and then simply kept going, outward and outward, into the dark. Voyager 1, in the late summer of 2012, crossed an invisible boundary called the heliopause, the place where the influence of our Sun finally gives way to the wider ocean of interstellar space. With that quiet crossing, it became the first object made by human hands to leave the protective bubble of our solar system altogether. To this day, it remains the most distant thing we have ever built, drifting now some 24 billion kilometers from home, and it is moving very fast by any human standard. Voyager 1 travels at roughly 17 kilometers every second. That is more than 60,000 kilometers in a single hour. It is fast enough to cross from one side of a continent to the other in mere seconds, fast enough that in the time it takes to read a single calm sentence, it has slipped farther from us than the length of a great city. By every measure of our ordinary experience, it is breathtakingly swift, and yet, set against the distance to the nearest star, it is almost heartbreakingly slow. If Voyager 1 were somehow aimed directly at Proxima Centauri, traveling at the very speed it travels now, it would take approximately 73,000 years to arrive. 73,000 years, longer than the entire span of recorded human civilization many times over. That is the gap. That is what 4¼ light years means when you translate it from a gentle-sounding number into the language of our fastest ships. Let us rest there for a moment with that thought before we go any further. The nearest star, the closest of all the lights in the sky, lies so far away that our most distant spacecraft would need a span of time longer than the rise and fall of every empire that has ever existed, simply to reach it. And it would arrive having sent back nothing, for it was never built for such a journey. It would simply pass by, cold and silent in the dark. Before we travel any deeper, it is worth taking a slow, gentle look at the place we are heading, because Proxima Centauri does not stand alone in the dark. It is part of a small family of stars, 3 of them bound together by gravity, known together as Alpha Centauri. The name itself comes from the brightest star in the constellation of the Centaur, and over time it came to describe the whole little group. 2 of those stars are the heart of the system. They are called simply Alpha Centauri A and Alpha Centauri B, and what makes them so striking is how familiar they would feel to us. They are both quite similar to our own Sun. Alpha Centauri A is slightly grander than the Sun, a touch more massive and noticeably brighter, pouring out about half again as much light. Alpha Centauri B is a little more modest, somewhat smaller and dimmer, with roughly 9/10 of the Sun's mass and about half its luminosity. These 2 stars are companions in the truest sense, circling one another in a long, patient, oval-shaped orbit that takes nearly 80 years to complete. As they move through that orbit, the distance between them slowly breathes in and out. At their closest, they draw to about 11 times the distance from the Earth to the Sun. At their farthest, they drift apart to some 36 times that distance, which is roughly as far as the Sun lies from distant, frozen Pluto. And from our vantage point here on Earth, they sit so near to each other in the sky that the unaided eye cannot tell them apart at all. They blur together into a single brilliant point, the third brightest star in all the night sky, a beacon that has drawn the gaze of southern stargazers for as long as there have been eyes to look up. The third member of this little family is Proxima itself, the dim red dwarf, far smaller and cooler than its two bright companions. It is bound to them by gravity, but only loosely, drifting around the central pair at a tremendous remove, some 13,000 times the distance from the Earth to the Sun. That is about a fifth of a light-year, a gulf so wide that a single slow orbit of Proxima around its two siblings may take anywhere from 500,000 to a full million years to complete. Imagine that for a moment with a calm and unhurried mind. A star so distant from its own family that it takes the better part of 1,000,000 years simply to circle them once. And of these three, it is Proxima, the small and quiet one that lies closest to us, which is why it sits at the center of nearly every dream we have ever had of reaching another star. And there is one more reason that Proxima draws our attention so powerfully, a reason that turns this story from a tale of distance into a tale of possibility. In the year 2016, a team of astronomers using a sensitive instrument in the dry, dark mountains of Chile announced that they had found a planet circling Proxima Centauri. They named it in the plain language of astronomy, Proxima Centauri b, and this planet is not some impossible giant or some scorched cinder. It is, by everything we can measure, roughly the size of the Earth, with a mass only a little greater than our own world. More remarkable still, it orbits within what astronomers call the habitable zone, that gentle band of distances around a star where the warmth is neither too fierce nor too faint, where liquid water might, in principle, gather and rest upon a surface without boiling away or freezing solid. A world about the size of the Earth, in the habitable zone, circling the very nearest star to our Sun. When that discovery was announced, the scientific community reacted with a careful blend of excitement and caution, and both of those feelings were entirely warranted. The excitement came from the sheer wonder of it, the thought that the nearest star of all might hold a world not unlike our own. The caution came from hard-won wisdom, the understanding that sitting in the habitable zone is necessary for life as we know it, but very far from sufficient. There is a great deal more to a living world than its distance from its star. And as we will see later in our long night together, the star in question, gentle little Proxima, carries some troubling habits of its own. But for now, let us simply hold the wonder of it. There is a planet there. We know that it exists, and it is the closest world to our own that we have ever found beyond the borders of our solar system. Now we come to the heart of the matter, the reason that the journey to the nearest star is not merely difficult but may be very nearly impossible. And the reason is not a flaw in our engineering. It is not something a clever generation will simply solve. It is a rule written into the deepest structure of the universe itself, a kind of cosmic speed limit that no amount of ingenuity can lift. To understand it, we travel back gently to the year 1905, to a young clerk in a patent office who, in his spare hours, was quietly rewriting our understanding of space and time. His name was Albert Einstein, and in that single year he published a theory he called special relativity. Among the many strange and beautiful consequences of that theory is a precise relationship between speed, mass, and energy. In our everyday lives, we imagine that if we simply keep pushing on something, it will keep going faster and faster without limit. Push a little, gain a little speed. Push twice as hard, gain twice as much. But the universe does not actually work that way, not at great speeds. As an object that has mass moves faster and faster, the energy required to make it go even faster does not grow gently and steadily. It grows faster than that, and faster still, climbing ever more steeply the closer the object comes to the speed of light. And as the object approaches that ultimate speed, the energy needed to push it any faster does not simply become large. It climbs toward infinity. Let us hold that idea softly, because it is one of the most important in all of physics. At 90% of the speed of light, a moving object behaves, to an outside observer, as though it has become more than twice as heavy as it was at rest. At 99% of light speed, that effect grows to about 7 times. At 99.9%, it swells to more than 20 times. And the energy needed to keep pushing climbs right along with it. To reach the speed of light itself, an object with any mass at all would require an infinite amount of energy. And infinite energy simply does not exist. There is not enough of it in all the universe, because the very idea of it is without limit. And so nothing that has mass can ever quite reach the speed of light. Not a spaceship, not a particle, not us. This is not a wall built by our limited tools. It is a wall built into reality. The universe itself forbids the crossing. There is a deeper truth still hidden inside this speed limit, and it is worth sitting with quietly. The speed of light is not merely the speed at which light happens to travel. It is, in a sense, the speed of cause and effect itself, the very rate at which one event in the universe can reach out and influence another. It is the fastest that any information, any matter, any flicker of energy can ever move from one place to another. It is woven into the structure of space and time so thoroughly that to break it would be to break the order of before and after, of cause and consequence. And so when we speak of this limit, we are not speaking of a technological frontier. We are speaking of the grain of the universe itself. Now, you might think that this is no great obstacle. After all, light itself crosses to Proxima Centauri in a little over 4 years. If only we could travel at even a fraction of that speed, the journey would shrink to something almost human in scale. And that is true, in a sense. But consider what even a modest fraction of the speed of light would actually mean. At 10% of the speed of light, which is about 30,000 kilometers every second, a journey to Proxima Centauri would still take 42 years in just one direction. Imagine setting out on such a voyage at the age of 30. You would arrive, if you arrived at all, at the age of 72. Your entire working life would have unfolded inside a spacecraft. Any children you left behind would have grown into middle age in your absence. The world you departed would have changed in 10,000 ways you could never have tracked from so far away. And all of that assumes a method of propulsion that we do not have, that we are not close to having, that does not exist anywhere outside the careful pages of scientific speculation. So let us be honest and precise about where we actually stand, with the very best that we have built. The fastest object that human beings have ever sent through space under its own power is a small, sturdy spacecraft called the Parker Solar Probe, launched in the late summer of 2018. Its mission is to study our own sun, to dive again and again toward the searing heat of the solar corona, using the sun's own immense gravity to whip itself to extraordinary speeds. At its closest approach, skimming just a few million kilometers above the surface of the sun, the Parker Solar Probe reaches a speed of nearly 700,000 kilometers an hour. That is around 190 kilometers every second. It is, without question, the swiftest machine our species has ever made. It is faster than any spacecraft that came before it, faster than anything else we have ever built and flung into the dark. And it is, for the purpose of reaching another star, almost touchingly inadequate. At that tremendous speed, a journey to Proxima Centauri would take approximately 6,500 years. Let us hold that gently against the span of our own history. Our fastest machine, aimed at the nearest star and traveling flat out, would take longer to arrive than the entire length of recorded human history. Everything we think of as the human story, from the first cities and the first written words right up to this very night. All of it would fit several times over inside the travel time of our swiftest ship to our closest stellar neighbor. That is the realistic starting point. That is the ground from which any dream of interstellar travel must begin to climb. And the gap between where we stand and what such a journey would require is not the kind of gap that closes through small, steady improvements. It will not be bridged by slightly better fuel, or stronger metals, or more careful planning of the route. To cross it, we would need propulsion based on entirely different principles than the burning of chemical fuel that has carried every rocket we have ever launched. We would need to reach into deeper sources of energy than any flame can offer. Several such sources exist, at least in theory, written quietly into the laws of physics, waiting. And as the night deepens, we will visit each of them in turn, slowly and without hurry, and we will see both the promise that each one holds and the great difficulties that stand in its way. The first of these deeper ideas was born in the late 1950s, in the years when the world was learning, with a mixture of awe and dread, what the atom could do. It was called Project Orion, and its central idea was as audacious as it was simple. If the burning of chemical fuel is too weak to carry us between the stars, then why not use the most violent energy release that humanity had ever harnessed? The plan was to build a great ship with an enormous, heavy plate at its rear, and then, one after another, to release small nuclear devices behind the ship and detonate them. Each detonation would slam against the massive plate, pushing the whole vessel forward. Great shock absorbers would cushion the blow so that the crew within would feel only a firm, repeated nudge rather than a fatal jolt. Explosion after explosion, thousands of them across the long voyage, would build the ship up to a meaningful fraction of the speed of light. It sounds almost like something from a strange dream, and yet the physics of it works. The numbers hold together. A large Orion-style ship could, in principle, reach perhaps 3 to 5% of the speed of light. At 4% of light speed, the journey to Proxima Centauri would take a little over a century, somewhere around 106 years. That is still far beyond a single human lifetime, but set it beside the 73,000 years that Voyager would need, and the difference is staggering. A century against 73,000 years. The leap is enormous, and yet Project Orion was never built, and it was not abandoned because the physics failed. It was abandoned for reasons that had nothing to do with the laws of nature, and everything to do with the realities of the world we live in. To fly such a ship would mean carrying thousands of nuclear devices into space and setting them off, one after another. In the early 1960s, the nations of the world signed a treaty that prohibited nuclear explosions in space, and no exception was ever carved out for the gentle purpose of propulsion. Beyond the politics, there were sober practical concerns. The sheer number of devices required ran into the thousands. The radiation released during the long acceleration would be deadly to any crew without immense shielding. And that shielding would add so much weight that it would deepen the very problem it was meant to solve. And so nuclear pulse propulsion became a quiet dead end, sound in its physics, impossible in our world, set aside and remembered now mostly as a bold idea from a bolder age. A gentler and more refined idea looks not to the explosive force of splitting atoms, but to the patient power that lights the stars themselves. This is fusion, the joining together of the lightest atoms under tremendous heat and pressure. It is the very process that powers our sun. Deep within the sun's core, hydrogen nuclei are pressed together so forcefully that they fuse into helium, and in that joining, a small amount of mass is converted into a great flood of energy. Our sun does this on a scale that is difficult to imagine, converting some 4 million tons of its own substance into pure energy every single second. and it has been doing so steadily for billions of years. The energy released for each small measure of fuel is vastly greater than anything chemical burning can offer. A fusion-powered rocket, if we could build one, would harness this same process, channeling the searing exhaust out behind the ship to push it forward at speeds far beyond any chemical engine. The faster the exhaust streams out the back, the more efficiently the fuel is used, and the more efficiently the fuel is used, the more speed a given amount of it can provide. In theory, a fusion rocket could carry us toward the stars at a meaningful fraction of the speed of light. The trouble is that we have not yet learned to tame fusion, even here on the ground, even in a laboratory that never moves at all. We have made fusion happen. We have, in brief and carefully controlled experiments, even coaxed out more energy than we put in for a fleeting moment. But a fusion reactor that runs steadily, reliably, hour after hour, producing more energy than it consumes, simply does not yet exist. The largest effort to bring such a thing into being is a vast international project under construction in the south of France, known by its initials, ITER. It is a research reactor, a great machine built to demonstrate that a self-sustaining fusion reaction producing net energy can truly be achieved. If it succeeds, it will mark a profound milestone in the long history of our species. But even then, it is a stepping stone, not a destination. The road from a research reactor to a working power plant on the ground is measured in decades. And the road from a power plant on the ground to a compact, reliable fusion engine that can run for 40 years in the cold vacuum of space without a single repair is longer still. We may walk that road one day. The physics permits it, but not soon and not without a great deal of patient work along the way. If fusion sits at the edge of what we might one day achieve, then antimatter sits at the very extreme of what the laws of physics will allow. To understand it, picture the ordinary particles that make up everything around you, and then picture their mirror images. For every familiar particle, there exists an antiparticle identical in almost every way but opposite in its electric charge. The mirror image of the electron is called the positron. The mirror image of the proton is the antiproton. And when a particle meets its antiparticle, something extraordinary happens. The two of them annihilate one another completely, vanishing in an instant and converting the entirety of their mass into pure energy. Not a fraction, not a sliver, all of it. 100% of the mass becomes energy. No other process we know of comes anywhere close to this. The burning of chemical fuel converts a tiny fraction of 1% of its mass into energy. The splitting of atoms, fission, converts less than a single percent. Even the fusion that powers the stars converts only a little more. But the meeting of matter and antimatter converts everything. The theoretical performance of an antimatter rocket is, on paper, simply stunning. A small quantity of antimatter, properly harnessed, could in principle push a spacecraft to a significant fraction of the speed of light. And yet, for all its theoretical beauty, antimatter remains perhaps the most distant of all our options, for two reasons that together seem almost insurmountable. The first is that antimatter does not exist in any useful amount anywhere in nature. There are no antimatter mines, no antimatter clouds waiting to be gathered. The only way we know to make it is in great particle accelerators, where high-energy collisions occasionally produce a few antiparticles at a time. The total amount of antimatter that all of humanity has ever produced, across every laboratory in every nation, throughout the entire history of the science, is measured in nanograms. Billionths of a single gram. At the rate we currently produce it, gathering together just 1 gram of antimatter would take millions of years. And a journey to another star might require not grams, but kilograms, perhaps even tons. There is no path we can presently imagine that would let us produce it at anything close to that scale. The second problem is even harder, and it is the problem of holding it. Antimatter cannot be allowed to touch ordinary matter, not even the walls of its own container, because the moment it does, both vanish in a flash of annihilation. It must be held suspended in a perfect vacuum, cradled away from every surface by powerful magnetic fields, with no margin for error at all. A single failure of that containment, anywhere at any moment, would mean catastrophic release. No system exists today that could hold large quantities of antimatter safely, and no one knows when, or whether, such a system might ever be built. Antimatter is the most physically perfect fuel imaginable, and at the same time the most technically remote. It is a dream of pure energy that we can describe in equations and cannot begin to hold in our hands. There is, however, a completely different philosophy of travel, one that sidesteps the whole troublesome question of carrying fuel at all. Instead of hauling along a heavy tank of energy, what if a ship could simply catch the push of light itself? This is the idea of the light sail. Light, though it has no weight in the ordinary sense, does carry a tiny push, a small parcel of momentum. When countless particles of light strike a smooth, reflective surface and bounce away, each one gives that surface the gentlest of nudges. A single particle of light pushes with a force too small to measure. But gather enough of them, falling upon a sail that is large and almost impossibly thin and light, and those countless tiny nudges add up into a steady, gentle, continuous acceleration. The most natural source of light to push such a sail is, of course, our own sun. A solar sail unfurls a vast, mirror-bright surface to catch the sunlight and is slowly pushed outward by it, needing no fuel at all. This is not merely theory. In the year 2010, a Japanese spacecraft named Icaros spread its great thin sail in the space between the planets and was carried gently along by the pressure of sunlight. It worked exactly as the physics promised. But the limitation of a solar sail is plain to see, for sunlight grows weaker the farther one travels from the sun. By the time a sail has drifted out past the orbits of the outer planets, the light from the sun has faded so much that its push becomes too feeble to matter. You cannot sail to another star on sunlight alone, because the wind that fills your sail dies away before the voyage has truly begun. And this is where a more daring idea takes shape. If sunlight grows too weak with distance, then why not build our own source of light, a source far more concentrated and powerful than the sun could ever be at such a range? Imagine a great array of lasers, built upon the ground or in space, all focused together into a single intense beam, aimed steadily at the sail of a departing ship. Such a beam could push far harder than fading sunlight ever could, driving the sail to tremendous speeds during the early stages of its journey, even as it raced away into the dark. This idea of laser-driven sails lies at the heart of the most serious and well-supported attempt, yet made to truly reach for the nearest star. It is called Breakthrough Starshot, and it was announced to the world in the spring of 2016. The effort was launched by a technology investor named Yuri Milner, a man who had once trained in theoretical physics before turning to the world of business, and who put a portion of his fortune toward the dream of touching another star within a single lifetime. The renowned physicist Stephen Hawking lent his voice and his name to the project as a public supporter until his passing in 2018. And the central idea is, in its way, both humble and breathtaking. Rather than building one great ship, Breakthrough Starshot imagines building tiny spacecraft, each one weighing about as much as a single gram, no heavier than a small paperclip. These miniature travelers, sometimes called star chips, would each be attached to a delicate sail only a few meters across and only a few billionths of a meter thick. A film of material so thin it would be almost invisible edge-on. A vast array of lasers on the ground, with a combined power of around 100 gigawatts, would focus its beam upon these sails for just a few minutes. And in those few minutes, drive them up to roughly a fifth of the speed of light. After that brief, fierce push, the lasers would fall silent, and the tiny probes would coast onward through the dark at that tremendous speed, carried by their own momentum across the long emptiness. At a fifth of the speed of light, the journey to Proxima Centauri would take a little over 20 years. The little probes would sweep through the system in a brief flyby, gathering what measurements and images they could in the short time available, and then turn their tiny instruments toward home and send the data back across the gulf with a small onboard laser of their own. That signal, traveling at the speed of light, would itself need more than 4 years to reach us. And so, from the moment of launch to the moment the first faint data arrived back on Earth, the whole endeavor would take around 25 years, assuming that every fragile and unprecedented piece of it, worked exactly as intended. It is important to be clear and gentle about what this is and what it is not. This is not a journey for human beings. It is not even close to one. It is a swarm of devices each the size of a postage stamp, racing at a fifth of light speed, carrying instruments smaller than a fingernail, with no way at all to slow down when they arrive. And yet, for all its modesty, it is real. It rests upon physics that genuinely exists, not upon wishful thinking. Research is being done. Technologies are being tested. The challenges, though, are immense and worth understanding so that we can appreciate both the boldness of the dream and the steepness of the climb. A laser array of 100 gigawatts represents a flood of power comparable to the entire electrical output of a fair-sized industrialized nation, all of it gathered together, perfectly synchronized, and focused upon a target that is already moving and accelerating away. The precision required to keep that beam fixed upon a sail only a few meters wide, from the surface of a rotating Earth, through an atmosphere that bends and scatters the light, lies far beyond anything our engineering can manage today. The sail itself must be reflective enough that it does not absorb the laser's energy and burn away, light enough to be pushed to such enormous speed, and yet strong enough to survive that violent acceleration without tearing apart. The little communicator aboard the probe must somehow send a measurable whisper of a signal across more than 4 light-years of darkness on the power of a device weighing a single gram. And the cost of building such a system runs into the billions, with a timeline measured in decades. But the work goes on. Papers are written, pieces are tested. The gap between what we can do today and what this would require is very real, and yet it is not obviously uncrossable. Whether the will to cross it will endure across the long years required is, perhaps, the harder question of the two. There is a layer of difficulty in all of this that the simple arithmetic of speed does not capture, and it is worth pausing over because it is so often overlooked. Suppose we solved every problem of acceleration. Suppose we found a way to drive a ship to a meaningful fraction of the speed of light. We would then immediately face a second problem, just as serious as the first, and it is the simple matter of stopping. A ship traveling at a tenth of the speed of light carries an almost unimaginable amount of energy in its motion, and all of that energy must go somewhere when the ship arrives. You cannot simply drift gently into orbit around a distant star the way a small capsule splashes softly down into the sea. At such speeds, to arrive at a star without slowing down would mean tearing straight through the entire system in a matter of hours, and continuing on into the void beyond, having seen almost nothing. To truly explore another world, to linger near it, to study it with care, you must shed all that tremendous speed. And here lies the cruelty of the physics. The energy required to slow down from a tenth of the speed of light is exactly equal to the energy that was required to reach it in the first place. If your ship runs on fuel that it carries, then you must carry twice as much, half for speeding up and half for slowing down. But that extra fuel adds weight, and the added weight requires still more energy to accelerate, which requires still more fuel, which adds still more weight. The problem feeds upon itself, growing without mercy. This compounding burden has a name and a long history. It was first described by a quiet, self-taught Russian schoolteacher named Konstantin Tsiolkovsky, who, more than a century ago, working largely alone, derived the fundamental relationship that governs all rockets. His equation reveals something both elegant and harsh. To gain a little more final speed, you do not need a little more fuel. You need exponentially more, the demand climbing ever more steeply the more ambitious your goal becomes. For the speeds required to travel between the stars, this relationship turns ordinary rocketry into an impossibility. To push even a modest payload up to 1/10 of light speed, and then to slow it down again at the far end, using the best chemical or nuclear engines we can imagine, would require a quantity of fuel so vast that it has no meaningful comparison in the real world. And so every serious plan for an interstellar mission either accepts that it can only be a flyby, carrying no fuel for stopping, or else relies on some clever way to slow down using forces found at the destination itself, rather than fuel brought from home. Several such ideas for slowing down do exist, each beautiful in its own way. One is the magnetic sail, sometimes called a magsail. The ship would unfurl a great loop of superconducting wire ahead of itself, creating a wide magnetic field. As the ship raced into the destination star's system, that magnetic field would catch the stream of charged particles flowing outward from the star, the stellar wind. And that gentle pressure would act as a kind of brake, slowly bleeding off the ship's enormous speed. The difficulty, when it comes to Proxima in particular, is that Proxima is a small red dwarf, and red dwarfs have thin and irregular stellar winds, except during their sudden flares. So the braking would be slow, perhaps taking years or even decades to bring the ship to a halt. Another idea imagines using a second laser beam from home, with the departing ship reflecting that light off a deployed mirror to push back against its own motion and slow itself down. The mathematics of it works on paper, but the precision required is extraordinary, and none of these systems has ever been built. Stopping at another star, it turns out, is a problem just as deep as reaching it in the first place. It receives less attention only because a simple flyby, while a far lesser achievement, is at least something we might manage somewhat sooner. Now let us turn, gently, to a different kind of difficulty altogether, one that no equation about fuel or speed can fully describe. Let us imagine for a moment that all the engineering problems were somehow solved. Imagine that a ship existed that could carry a crew of, say, 20 people across the void at 1/10 of the speed of light, on a journey lasting some 42 years. What would 4 decades in the deep darkness between the stars do to a human body and to a human mind? The first and most persistent threat is radiation, and it is also one of the least solvable. Here on the surface of the Earth, we are protected by 2 great invisible shields. The first is our planet's magnetic field, the magnetosphere, which deflects the vast majority of the charged particles streaming through space. The second is the atmosphere above us, which absorbs much of what slips through. The result is that, down here on the ground, the amount of radiation we receive each year from the cosmos is very small, a tiny fraction of what would otherwise reach us. Rise above the atmosphere to the orbit of the space station, and that exposure climbs considerably, even though the station still enjoys some protection from the Earth's magnetic field. Travel beyond that protection entirely, out into the open space between the planets, and it rises higher still. A crude journey to Mars, lasting only a matter of months in each direction, would expose its travelers to a dose far greater than anything we would ever permit for a worker here on Earth. But the deep space between the stars is harsher still than the space between the planets. Out there, beyond the reach of the sun's own magnetic influence, a constant rain of particles called galactic cosmic rays sweeps in from all directions. These are not gentle things. They are the nuclei of atoms, hurled across the galaxy at tremendous energies by the violent deaths of distant stars, by supernovae and other cataclysms scattered across the ages. The most energetic of these particles carry so much energy that almost no material can stop them. They would pass through meters of solid lead. They would pass through the hull of a spacecraft and through the bodies of anyone within, as though the metal and the flesh were barely there at all. A crew that spent 42 years adrift in interstellar space would gather a dose of radiation far beyond anything we would ever consider safe. The slow consequences would accumulate quietly over the years, raising the risk of cancer, clouding the lenses of the eyes, and perhaps harming the delicate tissues of the brain itself. Some fraction of such a crew would almost certainly fall ill along the way, and those who survived to reach the far star would arrive carrying the marks of their long exposure. This is not idle worry. It follows from everything we have learned about how radiation affects living things. Shielding helps, of course. Water, surprisingly, is among the most effective shields we have, because the hydrogen within it is good at absorbing certain kinds of radiation. A ship might wrap its crew quarters in tanks of water, serving the double purpose of protection and supply. But against the most energetic cosmic rays, no practical shield is enough. You can reduce the exposure. You cannot remove it. And 42 years is a very long time to live beside something you cannot escape. There is a second, gentler erosion that the long voyage would work upon the body, and it has to do with the simple absence of weight. Our bodies were shaped, over countless generations, to carry themselves against the steady pull of the Earth. Our bones hold their density because they are always bearing our weight. Our muscles keep their strength because they are always working against gravity. Take that pull away, and the body, ever practical, begins to let go of what it no longer seems to need. Bones grow thinner, muscles waste away. We have watched this happen to astronauts even on stays of just a few months aboard the space station, where, despite hours of daily exercise designed to fight it, they still lose measurable bone and muscle. Stretch that across 42 years, and even with the most vigorous routines, the damage would be severe. The solution to this, at least in principle, is both simple and elegant, and it has lived in our imaginations for a long time. If a section of the spacecraft were set spinning, then anyone standing along its inner wall would be gently pressed outward against it, and that pressing would feel to the body almost exactly like gravity. The writer Arthur C. Clarke described such spinning habitats with great clarity more than half a century ago, and the physics behind them is not in any doubt. A great ring or drum, turning at just the right pace for its size, would create within it a comfortable pull that the body would accept as the real thing. At a radius of 50 meters, a rotation of about 4 turns each minute would produce something very close to the gravity of Earth. This is achievable. The challenge lies only in the mechanical complexity of building and maintaining such a large rotating structure. The great bearings needed to let it spin smoothly against the still portions of the ship, and the weight all of this would add. But any serious crewed journey to the stars would almost certainly need to include some form of this gentle, manufactured gravity, lest the travelers arrive too weakened to stand upon the new world they had crossed so far to reach. And yet, of all the dangers the long voyage would hold, perhaps the most difficult is the one that lives not in the body but in the mind. 42 years inside a sealed vessel, with the same small handful of companions, surrounded on every side by an endless and indifferent dark. This challenge may be the hardest of all, not because we fail to understand it, but precisely because we understand it so well. And what we understand is sobering. For many years now, researchers have studied groups of people living in isolation and confinement, far from the wider world. They have watched the crews who winter over at remote Antarctic research stations, sealed in by the long polar night with no possibility of leaving until the season turns. They have studied submarine crew on deployments lasting many months in cramped quarters beneath the sea. They have run careful experiments in which volunteers are sealed inside simulated spacecraft for long stretches of time. One such experiment, carried out jointly by Russian, European, and Chinese researchers around the turn of the last decade, sealed 6 volunteers inside a mock spacecraft in Moscow for 520 days, recreating the psychological conditions of a journey to Mars and back. The findings from all these environments tell a consistent and quietly troubling story. Over time, friction between people tends to grow. The dynamics of the group grow rigid. Small irritations that would mean nothing in ordinary life swell into real sources of tension when there is no escape from one another and no fresh face to break the pattern. Sadness, anxiety, and disturbed sleep become common companions. Motivation begins to fade. Researchers have even identified a particular pattern they call the third quarter phenomenon, a noticeable dip in mood and cohesion that tends to arrive around the 3/4 mark of any long, isolated mission, the moment when the end is finally in sight yet still too far away to feel real, when the goal hovers tantalizingly ahead but remains stubbornly out of reach. Now imagine that pattern stretched across 42 years. The 3/4 mark of such a journey would arrive somewhere past the 31st year, 3 decades into the voyage. By then, the crew who had set out in their 20s and 30s would be approaching the age of retirement, having spent the whole of their adult lives inside a metal shell. Whatever friendships existed at the launch would have been tested by 30 years of unbroken closeness. Whatever quarrels arose along the way would have had 30 years to either heal or fester. To keep such a crew cooperative, functional, and whole across so vast a span would require a kind of social wisdom we have never had to develop. Governing structures that could survive across generations, ways of settling conflict that work under conditions of absolute confinement, and above all, a way to keep people striving toward a goal whose true reward none of them might ever live to see. No one has solved this, and it is not the sort of problem that a clever new machine can solve, because it is not a problem of machines at all. It is a problem of the human heart, and those are often the deepest problems there are. There is also the matter of staying connected to home, and here the long delays of light return to shape the experience in a profound way. Radio waves, like light, travel at the universe's ultimate speed, and so in principle, a ship could send messages back to Earth, and Earth could send messages out to the ship. But the delay grows with every kilometer of distance. At the moment when the ship is 1 light-year from home, a message would take a full year to arrive, and any reply would take another year to return. 2 years for the simplest exchange. By the midpoint of the voyage, the delay would stretch to more than 4 years for a single round trip. And at the destination, more than 4 years each way, so that the gap between asking a question and receiving its answer would be more than 8 years. That is not a conversation. That is not the kind of support a person can lean upon in a difficult moment. It is more like writing letters to a world that has already moved on by the time your words arrive, and that will have moved on again before any reply can reach you. And the Earth would indeed move on. In 42 years, the political map of the world would be redrawn many times. Technologies would turn over again and again. The crowds who cheered the launch would be replaced by people who grew up while the ship was still crossing the dark, people with no living memory of why the mission ever mattered. The institutions that built and supported the voyage might be reorganized, defunded, or dissolved entirely. In the strangest possibility of all, the very breakthrough everyone had been hoping for might arrive 20 years after launch, and a second, faster ship might set out and even arrive before the first one did, while the original crew, committed to the technology they left with, sailed on in ignorance, learning of it only years later when the news finally caught up with them across the light years. They would be the most isolated human beings who had ever lived, cut off not only from other people but from their own culture, from the living context that gave their journey its meaning, from any real hope of help. They would fly alone, and they would know it. There is one more thread of physics woven into all of this, and it is among the strangest and most beautiful that nature has to offer. It is called time dilation. When an object moves very fast relative to someone watching it, time itself does not pass at the same rate for both. The clock aboard the fast-moving object ticks more slowly than the clock of the one standing still. This is not an illusion, not a trick of measurement. It is a real and measured feature of the universe. We see it even in the satellites that drift overhead carrying our navigation signals, which move fast enough that their onboard clocks run very slightly slow compared to clocks on the ground. And we must correct for this difference constantly, for without that correction our navigation would drift astray within a single day. For a ship traveling at 1/10 of the speed of light, this effect is small. Over the 42-year journey, the crew would age only about 4 months less than the people they left behind. Barely noticeable, but push the speed higher and the effect grows dramatic and dreamlike. At half the speed of light, a journey that took some 8.5 years as measured from Earth would feel like only a little over 7 years to the crew. At 90% of light speed, the trip might pass in just over 2 years for the travelers, though nearly 5 would have passed at home. At 99%, the crew might age less than 8 months, while more than 4 years slipped by on Earth. And if a ship could somehow approach ever closer to the speed of light, the crew could, in principle, cross unimaginable distances within a single lifetime, while outside, billions of years quietly unfolded. The physics of this is entirely real. What breaks the dream is the energy required to reach those speeds, which makes even the antimatter problem seem gentle by comparison. But the deeper lesson is worth holding softly as you rest. The universe does not forbid a fast journey in the experience of the traveler. It only forbids a fast journey in the eyes of everyone watching from outside. The universe stays exactly the same size no matter how swiftly you move through it. You can make the journey feel shorter to yourself. You can never make it shorter for those you leave behind. Let us now imagine, gently, that a traveler did somehow arrive at Proxima Centauri. What would they find waiting for them there at the end of so long a road? The star itself is a red dwarf, small and cool, holding only about 1/10 of the sun's mass. Its surface glows at a temperature far lower than the sun's, which is why its light shines red rather than gold and white. Stars like Proxima pour out most of their energy in the deep red and the invisible infrared, and so the world it warms would be bathed in a dim, ruddy, perpetual twilight. If we were to replace our own sun with Proxima, the Earth would receive only a tiny fraction of the light it now enjoys, a fraction so small it is almost difficult to imagine. Perhaps a 2,000th of our present sunlight. Because Proxima shines so faintly, its habitable zone, the band where liquid water might rest upon a surface, sits very close to the star. The planet we have found, Proxima b, orbits at only about 7.5 million kilometers from its sun, completing a full year in just over 11 of our days. At such an intimate distance, A particular fate becomes almost certain over the long ages, and it is called tidal locking. When a planet circles so close to its star, the star's gravity tugs more strongly on the near side of the planet than the far side, and over a great span of time this gentle, relentless tugging slows the planet's spin until it turns exactly once for each orbit. The result is that one face of the planet comes to look forever toward its star, while the other faces forever away into the dark. Our own moon is locked to the Earth in just this way, which is why it always shows us the same familiar face. Proxima b is almost surely locked to its star in the same fashion. This creates a world of three distinct realms, unlike anything in our own experience. On one side lies an eternal day, where the dim red star hangs forever in the sky, never rising and never setting, casting its faint perpetual light. On the other side lies an eternal night, a frozen hemisphere that never sees its sun at all. And between them runs a ring of permanent twilight, the terminator, where the eternal day fades into the eternal night, a thin band of perpetual dusk encircling the whole world. Whether such a place could be habitable depends a great deal on its atmosphere. If the planet holds a thick enough blanket of air, that air might carry warmth from the blazing day side around to the frozen night side, smoothing out the extremes and perhaps leaving the twilight ring, and even parts of the dark hemisphere, gentle enough for liquid water to gather. But if the atmosphere were too thin, it might simply freeze and fall as ice upon the night side, collapsing entirely, leaving the world starkly divided between scorching light and bitter frozen dark. Which of these is true, we cannot yet say, for it depends on details of the atmosphere that lie beyond our ability to measure from so far away. And there is a further complication, one that casts a long shadow over the hope of life on Proxima b. The star Proxima is what astronomers call a flare star. From time to time, without warning, it erupts in sudden, violent bursts of radiation, flooding its surroundings with ultraviolet light and X-rays. During a major flare, the brightness of the star can leap by a factor of several hundred in the space of mere minutes. And Proxima b, orbiting so very close, would be drenched in radiation during each of these outbursts. The flares come often, perhaps several times in a single month, and over the long ages their cumulative effect would be severe. Whether the planet possesses a strong enough magnetic field to deflect this onslaught, the way the Earth's field shields us, is a question we cannot yet answer. The planet Mars, long ago, lost most of its atmosphere when its own magnetic field faded, leaving its air to be stripped away by the wind from the sun. A similar fate may have befallen Proxima b. Or perhaps not. Perhaps it holds a stronger field, or perhaps volcanic activity keeps replenishing the air it loses. We simply do not know. In truth, almost everything about Proxima b remains hidden from us. We did not see it directly. We detected it indirectly, by watching the tiny rhythmic wobble of the star itself, the slight tug that the planet's gravity gives to its sun as it circles, which shows up as a faint shifting in the star's light. From that gentle wobble, we deduce the planet's existence, its approximate mass, and the shape of its orbit, but we have never seen its face. We do not know its true size, nor what it is made of, nor whether it holds air or water or any feature at all that might welcome life. We know that it is there, and we know how it moves. Everything else remains, for now, a matter of careful inference and patient hope. There is, as it turns out, more than one world in that system. In the year 2022, astronomers confirmed a second planet circling Proxima Centauri, a small world named Proxima d, with a mass only about a quarter of the Earth's. It orbits even closer to the star than Proxima b, so close that it sits well within the searing radiation, almost certainly too harsh a place for life as we understand it. And there are hints, not yet confirmed, of still other planets in the system, smaller or more distant ones that lie at the very edge of what our instruments can detect. The method we use to find these worlds is far better at noticing planets that are large and close, because those tug most strongly on their star. Smaller worlds, or those farther out, are far harder to see. And so it remains entirely possible that somewhere in that nearby system, an Earth-like world circles quietly at a comfortable distance, undetected, simply waiting for instruments keen enough to find it. The same uncertainty hangs over the two bright sun-like stars. Alpha Centauri A and B both are similar enough to our own sun that rocky planets could well have formed around them. No planets have yet been confirmed there, but that is partly because the search is so difficult. The two stars circle one another, and their shared gravity creates zones where stable planetary orbits are possible and other zones where they are not. A planet close enough to either star or far enough from both could orbit steadily for ages. But in the troubled space between, the pull of the companion star would in time unsettle and scatter any world that tried to form. The search continues with ever more sensitive instruments. Great telescopes peer toward that bright double star, hunting for the faint signature of a world. A small dedicated space telescope was even proposed, named after an old astronomer of long ago, with the single purpose of watching Alpha Centauri A and B over many years from above the blurring atmosphere, searching patiently for planets. The possibility that a world much like our own circles one of those two familiar suns has not been ruled out. It remains, like so much in this story, an open and gently hopeful question. This brings us, softly, to one of the most haunting questions in all of science. A question first asked not in a lecture hall, but over an ordinary lunch. It begins with a man named Enrico Fermi, one of the great physicists of the last century, a man known not only for his brilliance but for a peculiar talent. He loved to make quick, rough estimates of things that seemed impossible to calculate, arriving at surprisingly good answers by combining small pieces of known information with clear thinking. One summer day, around the middle of the last century, while having lunch with colleagues, the conversation drifted toward reports of strange objects in the sky. After listening for a while, Fermi is said to have asked, almost offhandedly, a simple question that has echoed through astronomy ever since. Where is everybody? The full weight of that question takes a moment to settle, so let us approach it slowly. The universe is very old, around 13.5 billion years. Our own galaxy, the Milky Way, holds somewhere between 100 billion and 400 billion stars, and a great many of them are far older than our sun, by billions of years. Life arose on the Earth fairly quickly, once the conditions allowed it. So consider this gentle chain of reasoning. If life tends to arise wherever the conditions permit, and if some fraction of that life eventually develops intelligence, and if some fraction of intelligent life eventually develops technology, then by now there should be civilizations scattered across the galaxy that are not merely a little older than us, but billions of years older. And even travel between the stars at a small fraction of light speed, the very thing we have been calling so nearly impossible, would be enough, given billions of years, for such a civilization to spread across a large part of the galaxy. And yet when we look, we see nothing. No great structures built among the stars, no signals we can clearly read as the work of another mind, no visitors. No sign anywhere that the galaxy has been touched by the engineering of some older civilization. Fermi's quiet lunchtime question remains, after all these years, unanswered. And the proposed answers fall into a handful of gentle, sobering possibilities, none of them certain. Perhaps life itself is extraordinarily rare, a near miracle that happened here and almost nowhere else. Perhaps life is common, but intelligence is rare, requiring some unusual turn of fortune. Perhaps technological civilizations tend to destroy themselves before they ever reach the stars, through war or ruin or some accident of their own making. Perhaps travel between the stars truly is so hard that no civilization, however advanced, has ever managed to spread very far. Perhaps civilizations arise and simply choose, for reasons we cannot guess, never to expand. Or perhaps we are simply looking in the wrong way, listening for the wrong kind of signal. For decades now, in a patient and quiet effort, we have been listening. The search for signals from other civilizations has swept across more and more of the sky and more of the radio spectrum, year after year. And the result, very nearly, has been silence. Not quite total silence. There was once a strange and famous moment. On a summer night in the late 1970s, a radio telescope in Ohio recorded a signal of unexpected strength, lasting a little over a minute. Matching several of the qualities one might expect from a transmission sent across the stars. An astronomer reviewing the data later was so struck by it that he wrote a single word beside the printout, and that signal has been known ever since by that word. But it never came again. It has never been satisfactorily explained, and it has never been repeated, no matter how carefully we have watched the same patch of sky. Apart from that one tantalizing whisper, the heavens have stayed quiet, and that quiet has become one of the deepest mysteries we know. Proxima Centauri b sits right at the center of this great question. For if we ever did send even a small robotic probe to that nearest star, and if it found there any sign of life, whether long dead or still living, whether a single microbe or something grander, the implications would be staggering. To find life arising twice, independently in the same small corner of one galaxy, within 4 light-years of one another, would suggest that life is not rare at all, but common. Perhaps written into the very chemistry of the cosmos. And yet strangely, if life is common, then Fermi's question grows sharper rather than softer. For if the galaxy teems with life, then why is it so silent? The nearness of Alpha Centauri makes it not only a destination but a clue, a place where we might one day begin to answer the oldest question we have ever asked of the night sky. It helps sometimes to set this great difficulty against the long story of human exploration, where again and again, a journey that once seemed simply impossible became, in time, merely difficult. And then ordinary. For most of human history, the idea of sailing all the way around the world was not even attempted, because it was unimaginable. No ship, no chart, no knowledge of what lay beyond the known coasts made it seem possible. Then in the early 16th century, an expedition set out to attempt the crossing, and after years at sea, a single battered ship returned, having circled the entire Earth. Most of those who set out did not survive. The achievement came at a terrible cost, but it was done, and once it was done, the whole sense of what was possible shifted. Within a few decades, voyages across the great oceans became almost routine as the knowledge and the confidence spread. Or consider the dream of flight. For all of human history, people watched the birds and longed to join them and could not. Then, on a cold morning in the very early years of the last century, 2 brothers lifted a fragile machine of wood and cloth off the sand for 12 seconds, covering a distance shorter than the wingspan of a large aircraft today. Less than 50 years later, machines were breaking the sound barrier. Less than 70 years after that first brief hop, a human being walked upon the surface of the moon. The whole arc, from the first powered flight to the first footprint on another world, unfolded within the span of a single human lifetime. There were people alive who remembered the first flights and lived to watch the moon landings. These stories are not proof that travel between the stars is just around the corner. The physics of crossing the gulf between stars is of an entirely different order than the physics of flight within an atmosphere, or even of travel within our own solar system. The leap is far greater. But these stories do remind us, gently, that the distance between impossible and possible can sometimes close with surprising speed. Once the right understanding and the right tools finally come together. The real question for interstellar travel may not be whether such a thing can ever be done, but when. The physics does not say no. It says, instead, something more patient and more open. It says not yet, and it waits to be persuaded otherwise. In the meantime, even from where we stand, our ability to study these distant worlds has grown remarkably. A great new telescope, fully at work since the middle of 2022, has opened entirely new windows on the universe. Among its gifts is the ability to study the atmospheres of distant planets through a clever trick of starlight. When a planet passes directly in front of its star as seen from the Earth, a small portion of the starlight filters through the planet's atmosphere on its way to us. Different gases drink up different colors of light, and so by carefully studying which colors are missing, astronomers can read the chemistry of an atmosphere across the vast distances of space. This telescope has already detected the signatures of various gases in the air of faraway worlds, the first true steps toward understanding the atmospheres of other planets. But Proxima b presents a difficulty of simple geometry. From our particular vantage point, the planet does not appear to pass in front of its star. Its orbit is tilted in such a way that, from the Earth, it never crosses the face of Proxima, and so this method of reading its atmosphere is closed to us. Other instruments, though, may yet succeed where this one cannot. A new generation of enormous telescopes is being built, including one in the mountains of Chile with a primary mirror nearly 40 meters across, large enough that it might one day directly catch the faint light reflected from the surface of Proxima b itself. This is extraordinarily difficult, for the planet would be many thousands of times fainter than its star, lost in the glare like a candle beside a searchlight. But if it can be done, the reward would be immense. We might learn the composition of the planet's air, the reflectiveness of its surface, perhaps even hints of liquid water, perhaps even the faint chemical fingerprints that life leaves behind. Not certainty, but real knowledge, narrowing the wide field of possibilities. We might finally learn whether Proxima b is a living candidate for habitability or a barren and ruled-out world. That knowledge alone would reshape the whole conversation about whether the journey is worth attempting. If Proxima b turned out to be plainly dead, the urgency would fade, and the nearest truly promising world might lie dozens or hundreds of light years away. But if Proxima b showed the unmistakable signs of an atmosphere rich in the gases that, on Earth, are produced by living things, then the question would become something else entirely. Something that no generation before us has ever had to face. It is worth holding for a moment just how recently all of this knowledge has come to us, because it places our impatience in a gentler light. For the overwhelming majority of the time that human beings have existed, the stars were simply lights in the sky. People knew that they moved in patterns. They named the patterns and used them to find their way and to mark the turning of the seasons. They filled the spaces between the stars with stories and gods and meaning. But they had no notion of what the stars truly were, no sense of how far away they lay, no understanding that those points of light were other suns, some of them not so different from our own. The realization that the stars are suns came only after the scientific revolution. And the first measurement of the distance to any star beyond our sun came only in the 1830s, when an astronomer succeeded in measuring the tiny wobble of a star called 61 Cygni and calculated, for the first time, the true distance to another sun. From that single measurement, the scale of the universe began, slowly, to come into focus. Within a few decades, Proxima itself was measured and found to be our nearest neighbor. Within a century, another astronomer had shown that the faint smudge we call Andromeda was not a cloud within our own galaxy at all, but an entire separate galaxy, lying some 2.5 million light-years away. In the space of about 100 years, the universe in our understanding grew from a small dome of fixed lights into an almost incomprehensibly vast structure, holding billions of galaxies, each one cradling hundreds of billions of stars. We have known that Proxima Centauri is a separate sun for only a little more than a century. We have known that it holds a planet for less than a decade. We have been seriously dreaming of missions to the stars for only about 60 years, and we have not yet sent anything at all. On the long timescale of our species, the time since we first began to think seriously about reaching the stars is barely the blink of an eye. There is a particular quality to the distance to Alpha Centauri that sets it apart from the other great numbers of astronomy. The distance to the Andromeda galaxy, 2.5 million light-years, fills the mind with awe at the scale of the cosmos, but it carries no sting of personal frustration. We never expected to go there. It lies far beyond any horizon of planning we could ever draw, but 4.25 light-years is different. It is the nearest star, just outside the door of our own solar system in the most literal astronomical sense. It is close enough that a spacecraft has, by accident, already been drifting in its general direction for decades. Close enough that real engineers have sat down and calculated real plans to reach it. Close enough that a funded effort exists with the specific aim of sending a probe across the gap. Close enough that the world circling Proxima feels, somehow, as though it ought to be reachable within a human lifetime, or at least within a few of them, if only we tried hard enough. And that is the gentle ache at the center of this whole story. The physics makes it so very hard, not impossible, but so hard. So many things must come together, all at once, in a way that has never been achieved before. The propulsion, the materials, the biology, the psychology, the vast and patient engineering, the political will, the funding sustained across generations, all of it converging. The distance to Alpha Centauri is close enough to feel as though it should be within reach, and far enough to defeat every attempt we have made so far. It is the precise distance that marks the boundary between a civilization confined to a single solar system and a civilization that has touched the stars. We stand on one side of that line. Everything else in the universe lies on the other, and between us and the nearest point of that other side stretch 40 trillion kilometers of vacuum, cold, radiation, and silence. There is another way to think about this whole problem, and it is a quieter, more patient way. Rather than asking how to build a faster ship, we might ask whether we could simply accept a slower one and design it not to carry a single crew, but to carry whole generations. This is the idea of the generation ship, and it has a strange and somber beauty to it. The vessel would be enormous, large enough to hold a self-sufficient community of human beings for the entire duration of the voyage. Not 20 people lasting 42 years, but perhaps hundreds or even thousands of people across many decades and many generations. The ship would be launched by one generation, and the journey would be completed by their distant descendants. The people who finally arrived at Proxima Centauri would have no personal memory of the Earth at all. They would have been born aboard the ship, raised aboard the ship, and would know no other world than the curved metal sky above them. A generation ship solves certain problems even as it creates others. It quietly resolves the matter of any single person surviving the whole long voyage, because the population would renew itself, the young replacing the old. Life continuing across the years as it always has. It keeps the mission alive across the generations, so that no individual need bear the impossible weight of an entire 40-year journey. But it raises questions of a different and deeper kind, questions that touch on the very meaning of choice and consent. The first generation would choose to go, but the generations that followed would never have chosen at all. They would simply be born into a mission they could not refuse, confined to a sealed world they never selected, on a journey that would consume their entire lives. Whatever structures of society and governance existed at the launch would, in time, be questioned, reinterpreted, or abandoned by descendants who had no connection at all to the founding moment. We have, in the long history of our species, only a few faint parallels to draw upon, and none of them is truly close. The most isolated human communities that have ever existed are the populations of remote islands, cut off for many generations from the rest of humanity. And yet even they had occasional contact with the wider world, and even they knew that a wider world existed somewhere beyond the horizon. The people aboard a generation ship would have neither. Their entire universe would be the ship itself, its corridors and chambers their whole inheritance. What that would do to human culture, to human identity, to the shape of human society, we cannot fully say because we have never done it and cannot fully predict it. The ethical weight of bringing into existence people who have no choice but to live and to die within a sealed vessel, flying through an endless dark, is not some minor footnote to the idea. It sits at its very center, and the serious thinkers who have studied interstellar travel have never resolved it. And there is the further question of what would happen at the journey's end. The community aboard, whatever it had become across the generations, would have to make a profound transformation, leaving behind the only existence any of them had ever known. The existence of a ship, and learning instead to make a home in an utterly alien star system. The skills honed across generations for maintaining a vessel might not transfer at all to the work of settling a world. The social patterns that had evolved for life in a sealed container might simply fail upon open ground. The descendants of the original crew might feel a deep love for the ship that had always been their home, and a strange unease toward the destination their ancestors had chosen for them. Generation ships, then, are not a complete answer to the problem of reaching the stars. They are a different set of problems, and some of them may be harder still than the ones they were meant to solve. There is one more approach, gentler in its way, that would sidestep the troubles of the generation ship entirely. What if, rather than living through the long journey, a crew could simply sleep through it? If human beings could be placed into a state of deep suspended animation, their bodies slowed almost to stillness. Then the biological and psychological trials of a 42-year voyage would compress, from the sleeper's point of view, into the briefest of intervals. They would close their eyes near the Earth and open them, seemingly moments later, beneath the red light of another sun. They would not have aged. They would not carry the long weight of those years. The people who arrived would be the very same people who left, unchanged by the crossing. This is a beautiful idea, and it lives in countless stories. But true suspended animation of that kind does not yet exist, and it is worth being honest and precise about how far we are from it. There is a medical technique, used today, in which a patient's body is cooled to slow its processes and protect the brain during certain emergencies and surgeries. This is real and it works, and patients are cooled and then gently rewarmed and recover, but the slowing it achieves is modest. The body's processes slow only somewhat with each degree of cooling, and at the temperatures we can safely reach, the body is still very much alive and active, merely a little quieted. It is nothing like the deep stillness that a voyage to the stars would require. To approach true stillness, one would need to cool the body far more profoundly, and there the great obstacle appears. As water within living tissue approaches the freezing point, it begins to form ice crystals, and those crystals are sharp and destructive at the smallest scale, piercing the delicate membranes of cells and tearing apart the fine structures within. There are clever ways around this in small measure. Certain protective chemicals can replace some of the water in cells and discourage the formation of ice, a process of cooling so rapid that water hardens into a glassy solid, rather than crystals can preserve some biological structures. We can already preserve and later revive certain cells, and small samples of life, and even whole organs in the laboratory have been cooled in this way and rewarmed with their function intact. But a whole human being, with all the vast complexity of the body, the intricate web of blood vessels, the unimaginable tangle of connections within the brain, has never been preserved in this way and brought back. The difficulty grows enormously with the size and complexity of the living thing, and a human being is among the most complex things we know. The research continues, carried forward by people motivated partly by the hope of future medical good, and partly by the quiet recognition that any realistic journey to the stars would almost certainly need it. But we are far from a working system, and even if we one day learn to still and revive a human being, the spacecraft carrying its sleeping crew would still need to operate entirely on its own for 42 years, tending the preservation systems, maintaining the environment, keeping everything functional until the distant moment of waking. No machine we have ever built has run for 42 years in space without human hands to tend it. The Voyager probes have endured for nearly 50 years now. It is true, but they are vastly simpler than a vessel built to carry sleeping people. And even they have always had a team on Earth watching over them. A crewed ship sailing beyond all reach of help would need a level of self-sufficiency, of self-repair, of judgment in the face of the unexpected that exceeds anything we have made. The margin for error would be zero. A single quiet failure, a backup that did not engage, a slow cascade of small malfunctions across the decades, any of these could be fatal to a crew who slept and could not wake to notice. Self-healing systems and an artificial intelligence wise enough to manage the full complexity of a ship across the years would be necessary companions on such a voyage. Neither yet exists at the level such a journey would demand, and so every path we explore leads gently to the same quiet place. More must be learned, more time is needed. More breakthroughs must come. The distance does not shrink while we wait, but our ability to imagine crossing it does grow, slowly, year by year, paper by paper, idea by idea. It is worth lingering, too, on the mathematics that makes ordinary rocketry so hopeless for this task, because understanding it brings a strange kind of peace, a sense of why the universe sets the terms it does. The relationship discovered by Tsiolkovsky long ago tells us that to gain more final speed, a rocket needs an ever larger share of its mass to be fuel, and the demand grows not gently but explosively. For the kind of fuel that ordinary rockets burn, the joining of hydrogen and oxygen, the exhaust streams out at only a few kilometers per second. To reach even a tenth of the speed of light using such fuel, you would need a quantity of it so vast that it has no meaning in the real world. The entire observable universe does not contain enough hydrogen to do it. This is why chemical rockets cannot carry us to the stars. Not that they will not with enough effort, but that they cannot, as a matter of simple arithmetic. The numbers forbid it absolutely. The only escape is to find a way to send the exhaust out far faster, or better still, to stop carrying the fuel at all. Nuclear engines that heat their propellant with the warmth of a reactor do a little better, but still fall hopelessly short. Ion engines, which fling charged particles out the back using electric fields, do better still, yet remain far too weak for the stars. Fusion engines, with their theoretically tremendous exhaust speeds, begin at last to look genuinely possible, The required mass is large but not absurd. And the laser sail, that elegant idea, escapes the tyranny of the rocket equation altogether, for it carries no fuel at all. All the energy stays behind on the ground, where weight is no obstacle, and the ship needs only to be as light as a leaf, catching the push of the beam. This is why the laser sail is so compelling to those who study these things, even with all its formidable engineering challenges. It is the one approach that slips free of the exponential burden that crushes every other. Let us widen our gaze for a while, away from the single star and out toward the galaxy that holds it, for Alpha Centauri is not only our nearest neighbor. It is also a single quiet data point in a vast statistical story about what the Milky Way truly contains. Our galaxy is a great spiral, a slowly turning wheel of stars roughly 100,000 light-years across and a few thousand light-years thick through most of its breadth. At its center sits an enormous black hole with the mass of some 4 million suns, around which the whole grand structure turns. The galaxy holds somewhere between 100 billion and 400 billion stars, and about half of them are small, cool, long-lived red dwarfs, much like Proxima. A great many others are gentle orange and yellow suns, not so different from our own. The rare blue giants blaze brilliantly and die young, collapsing within a few million years. And more than half of all stars, it seems, do not travel alone at all, but in pairs or larger families, circling one another under their mutual gravity. Just as Alpha Centauri's two bright suns and their dim red companion do. In this, our nearest neighbor is utterly ordinary. There is nothing about it that sets it apart from countless other systems scattered throughout the galaxy. And our own sun, a solitary yellow star drifting some 26,000 light-years from the galactic center, is also entirely ordinary. We circle the heart of the galaxy at a stately pace, completing one great orbit roughly every 225 million years. The last time the Earth occupied this same position relative to the galactic center, the age of the dinosaurs had not yet truly begun. We are, in every measurable way, an unremarkable world orbiting an unremarkable star in an unremarkable corner of a typical galaxy. And that very ordinariness is, in its way, the most significant fact of all. For if conditions around an ordinary star in an ordinary place gave rise to life, and eventually to minds capable of looking up and wondering, then the sheer number of similar places throughout the galaxy is staggering. There are tens of billions of red dwarfs. There are tens of billions of sun-like stars, and we have learned only in recent decades that planets are not rare at all. The first confirmed planet found orbiting a sun-like star beyond our own was discovered in the mid-1990s by two Swiss astronomers who detected a great gas giant circling extraordinarily close to its star, a kind of world no one had expected to find. That single discovery opened a floodgate. Over the following 3 decades, the hunt for planets around other stars became one of the most fruitful endeavors in all of astronomy. A dedicated space telescope stared without blinking at a single patch of sky, holding many thousands of stars, watching for the tiny dimming that occurs when a planet passes across the face of its sun. It found thousands of worlds, and from the careful study of all that data came a conclusion that still has the power to take the breath away. On average, every star in the Milky Way has at least one planet. Some have many. The galaxy holds, by this reckoning, hundreds of billions of planets, and a significant fraction of the sun-like stars and red dwarfs have worlds resting within their habitable zones. Even by cautious estimates, that means tens of billions of potentially habitable worlds in our galaxy alone, tens of billions of possible homes, and yet we listen and we hear nothing. This is the heart of the great silence, the very paradox that Fermi gestured toward over his lunch so long ago. The numbers seem to demand that life should be everywhere. The silence seems to insist that, if it is not speaking. And the distance to Alpha Centauri, the nearest of all the steps we might take into that crowded and silent galaxy, stands as a quiet reminder of how isolated each of those billions of worlds truly is. For even if every star has its planets, and even if many of those planets could harbor life, each one is separated from the next by light years of empty dark. The nearest possibly habitable world beyond our own solar system is Proxima b, 4¼ light years away. If there is life there, it has never spoken to us. And if we wish to know whether it is there at all, we must go. And going is the one thing we cannot yet do. It is worth remembering, as the night deepens, that we have only been trying seriously for about 60 years, and that the people who work on this are real, patient, careful people, not dreamers spinning fantasies. In the years around the late 1970s, a group of engineers in Britain carried out a rigorous study of a fusion-powered probe that might one day be sent to another nearby star. They named the project after a figure from old mythology, and they worked through the engineering in earnest detail. They concluded that such a probe, unmanned and built only to fly past its target without slowing, might reach a neighboring star in around 50 years of travel. The fuel they favored was a rare form of helium, found only in tiny amounts in the wind from the sun and scattered sparsely across the surface of the moon, so that gathering enough of it would itself have demanded a great enterprise of mining and processing in space. Their probe was never built and was never meant to be. It was an exercise of the mind, a careful proof that such a mission was not forbidden by physics, only made formidable by engineering. That study was later revisited and updated by a new generation, in an ongoing collaborative effort to bring the old analysis into line with our modern understanding. And other groups have continued to produce serious technical work on missions to the stars, year after year. This is a small community, but a dedicated one, doing genuine physics and genuine engineering at the very edge of what the universe permits. And 60 years, it is worth remembering, is a very short time. Consider that the splitting of the atom was first demonstrated in the late 1930s, and the first nuclear power plant began producing electricity only 16 years later. Consider that the first programmable electronic computer began its work in the middle of the last century, and that the worldwide network we now take for granted became publicly accessible only about 45 years after that. In one technology after another, the gap between the first glimmer of an idea and its practical reality tends to be measured in decades, not centuries, once the foundational science is in place. For travel to the stars, much of that foundational science is already in place. The physics is understood. What is missing is the engineering to make it real. Fusion, the most promising of all the propulsion ideas, has had its underlying science understood for many decades. What it lacks is the practical ability to run a controlled, sustained, energy-producing reaction, and that ability is slowly being developed. Whether it will mature in time to carry us to the stars within this century, no one can say, but 60 years of serious thought is not nothing. In the long perspective of history, it is barely the beginning. There is yet another layer of difficulty that even the cleverest propulsion would have to face, and it lives in the very emptiness of interstellar space. An emptiness that turns out not to be quite as empty as it seems. The space between the stars is filled, very thinly, with a faint scattering of gas and dust, the interstellar medium. Our own solar system happens to drift within a region of slightly thicker, warmer gas, sometimes gently called the local cloud, which sits inside a much larger bubble in the medium. A vast cavity, perhaps 300 light-years across, thought to have been carved out long ago by the explosions of dying stars. Alpha Centauri, as it happens, lies within the same local cloud as we do. The two systems are embedded in the same diffuse pocket of gas, neighbors not only in distance, but in the very material that surrounds them. This gas is extraordinarily thin, far thinner than the best vacuum we can create on Earth, only about a tenth of a single hydrogen atom in each cubic centimeter of space. And yet, for a ship traveling at a tenth of the speed of light, even this whisper of matter becomes a hazard. The ship would be plowing through that thin medium at tremendous speed, and the countless tiny impacts of individual atoms would, over 4 light-years of travel, slowly wear away at the leading surfaces of the craft. The faster you go, the more each impact carries, and over the long journey the front of the ship would be gradually abraded, as though sandblasted by the gentlest of cosmic winds. The answer is to place a thick shield at the front, something expendable to absorb the impacts and protect the ship behind it. But that shield adds weight, and as it erodes it must be replaced, which means carrying spare material, which adds yet more weight, and so the old compounding problem returns once more. And there is a rarer but graver danger. The void between the stars is not entirely free of larger debris. There are dust grains and small fragments of rock and pieces of matter long ago cast out from other star systems, drifting silently through the dark. The chance of striking one at random is low. But over 4 light-years of travel, low is not the same as 0. And at a tenth of the speed of light, even a grain of sand carries the energy of an artillery shell, while a small pebble would be catastrophic. A ship would need some way to detect and avoid such debris, and whether sufficient warning and deflection could ever be achieved is an open question, one without an obvious answer. It is simply one more layer in the great stack of challenges that the distance to Alpha Centauri quietly presents. None of them, taken alone, is plainly impossible. But together they form an engineering problem unlike anything our species has ever attempted. It is worth remembering, too, that the people who carry this work forward are not figures from a story. They are real men and women with offices and salaries, who write grant applications and attend conferences, who publish careful papers and argue with one another about the fine details of mass ratios and exhaust velocities and the containment of plasma. There are foundations devoted entirely to the study of flight between the stars, publishing journals that have run for the better part of a century. There are annual gatherings where engineers and physicists come together to share their work on this single distant dream. There are organizations dedicated to moving the idea of interstellar flight, step by careful step, from pure concept toward eventual reality, running working groups on propulsion, on life support, on the design of missions, and even on the difficult human questions of a voyage lasting decades. The privately funded effort to develop laser-driven sails has employed real engineers to advance the technology. And space agencies have funded studies of precursor missions, spacecraft designed not to reach another star, but to travel deep enough into the space between the stars to study the medium itself and to test the technologies that any true interstellar mission would one day need. One such concept, studied carefully by a respected laboratory, envisions a spacecraft that would travel 1,000 times the distance from the Earth to the Sun, deep into interstellar space, within about 50 years. That is still only a tiny fraction of the way to Proxima Centauri, perhaps a 63rd of the journey. But it would carry us dramatically farther than the Voyager probes have gone, and it would send back precious knowledge from the deep dark that would inform every mission that came after. These are not the activities of dreamers at the fringe. They are serious science and serious engineering, carried out by serious people at serious institutions. The problem of reaching the stars is not ignored. It is being worked, slowly, with far less funding than its importance deserves, across long timelines and uncertain outcomes, but it is being worked. And the work compounds. Each paper builds upon the last. Each careful analysis reveals the next layer of problems to be solved. Each solution lays a foundation for the next attempt. The distance to Alpha Centauri is exactly what it was when Robert Innes first measured it more than a century ago. But our understanding of how we might one day cross it has deepened immeasurably in the centuries since. Not enough to do it yet, but meaningfully more than nothing at all. There is a quiet and beautiful fact about our presence in the cosmos that deserves a place in this long night, and it concerns something we have already sent toward the nearest star, entirely without meaning to. Light and radio waves travel at the same ultimate speed, and human beings began broadcasting radio waves into the air, and thus inevitably out into space, more than a century ago. The first faint radio transmissions began in the early years of the last century, and the first powerful, deliberate broadcasts followed in the decades after. Every one of those signals, once it left the Earth, kept traveling outward in all directions at the speed of light, never stopping, spreading ever wider into the dark. And so a radio signal sent 100 years ago has now traveled 100 light years out into the galaxy in every direction. Proxima Centauri lies only a little over 4 light years away, which means that every radio broadcast, every television signal, every radar pulse we have ever sent, going back to the very earliest, has long since passed through the Alpha Centauri system and continued on beyond it. Our electromagnetic presence, the faint glow of our civilization's chatter, reached the nearest star many decades ago. What, if anything, was there to receive it, we have no way of knowing. If anyone or anything was listening, we would not learn of any reply for at least another 8.5 years after it was sent, and only then if a reply were sent at all, and only if there were anyone there to send it. We have, in a sense, already said hello to Alpha Centauri, not by intention, but simply by living and speaking and filling our own skies with signals. The light of our existence reached that star long ago. What it did not carry with it was any means for us to follow. The signal went on ahead, racing through the system and out into the wider galaxy. And we remained here, still on this single world, still working out how we might one day cross the gap ourselves. It helps, sometimes, to bring this vast distance back to a human scale, to set it beside the one journey beyond the Earth that we have actually made. The distance from the Earth to the Moon is a little under 400,000 kilometers, and that remains the farthest any human being has ever traveled from this planet. The astronauts of the great lunar missions crossed it in about 3 days. The Moon is the only other world that bears the print of a human foot. A small handful of people have walked upon it, and none have returned for more than half a century. Now, the distance from the Earth to Proxima Centauri is about 100 million times greater than the distance to the Moon. Let us hold that gently with a small thought experiment. Imagine shrinking the entire Earth-Moon distance down to a single meter, the length of a long stride. On that scale, where the Moon sits just 1 meter away, Proxima Centauri would still lie more than 100,000 kilometers off, which is roughly a quarter of the real distance to the actual Moon. The nearest star, in a model where the Moon is only a meter away, is still a quarter of the way to that same Moon. The universe is built at a scale that makes all of human travel feel like the smallest rounding error. And yet, we went to the Moon. We crossed that gulf only 12 years after the first time a human being orbited the Earth, only 66 years after the first powered flight lifted off the sand. The pace of that acceleration, across a single century, was unlike anything in any prior age of human history. Whether it was a feature of that particular century, driven by forces that may not last, or whether it reflects something deeper and more lasting about the trajectory of a technological species. No one can say with certainty. If it was only a passing feature of one remarkable century, then the future of travel to the stars is deeply uncertain. But if it reflects something more fundamental, then the distance to Alpha Centauri may, in practical terms, prove shorter than it appears tonight. No one knows the answer. But the question is real, and it is among the most consequential our species has ever faced. If we ever do send something across that gulf, and if it finds something waiting there, the question that follows immediately is simply, what then? And the answer depends entirely on what is found. We can imagine, softly, a few different futures. In one, Proxima b turns out to be barren, a rocky world with little or no air, no sign of water past or present, its surface blasted bare by the star's relentless flares. Even then, the discovery would be precious, for any close knowledge of a world beyond our solar system would be unprecedented. But the urgency to follow would fade, and the search for life would move on to more distant and more promising worlds. In another future, Proxima b is found to hold an atmosphere, and perhaps the shimmer of liquid water, with no clear sign of life but with habitability genuinely plausible. That would be a compelling result, and the pressure to send a more capable probe, one able to study the world in greater depth, would grow intense. The timeline would still be measured in decades, but the goal would be clear and bright. In a third future, the probe detects the actual signatures of life. Perhaps certain gases together in the atmosphere that should not coexist unless something living kept replenishing them. Perhaps complex molecules arranged in pattern that no lifeless chemistry could easily produce. This would be, without qualification, the most significant scientific discovery in the whole of human history. Confirmation that life exists somewhere beyond the Earth. The implications for science, for philosophy, for our deepest sense of who we are and whether we are alone, would be beyond anything we have known. And in the strangest future of all, the probe might find something that does not fit the natural categories at all, something that appears, somehow, to have been made. Evidence of another mind at the nearest star. No one has truly planned for that. The response would be unpredictable, immediate, and global, and that 40 trillion kilometer gap would suddenly feel entirely different. Not abstract, not philosophical, but concrete and close. There is something there, it would say, and it is very near, and we can barely reach it. That alone would change the conversation forever. We have now wandered, slowly and without hurry, through this single distance from many different directions, through the physics, which is unbending, through the engineering, which is daunting, through the biology of the body and the fragility of the mind, through the long history of our exploration and the quiet statistics of the galaxy, through the study of distant worlds and the deepest questions of philosophy. And what emerges from all of it is a picture that is, at once, sobering and strangely hopeful. The distance is real. The physics cannot be argued with. The challenges are not small problems waiting for a clever trick. They are large, deeply interconnected, and in some cases unsolved at the most fundamental level. And yet, through all of it, the universe never quite says no. Every single technical challenge has, in principle, a physical solution. Fusion is real, a genuine phenomenon that lights the stars themselves. The challenge is only to engineer it reliably and at the needed scale. Time dilation is real, and the physics permits travel at relativistic speeds. The challenge is only to reach those speeds. The preservation of living tissue is partly real, for cells and organs can already be preserved. The challenge is only to scale it to a whole human being and to reverse it safely. Autonomous spacecraft are real, for the Voyager probes have endured in the dark for nearly half a century. The challenge is only to build something far more complex that can do the same. None of these is a mystery. They are engineering problems of extraordinary difficulty, and engineering problems throughout our history have tended to yield, sooner or later, to the patient application of intelligence and resources. The real question for travel to the stars is not whether the laws of nature forbid it, for they do not. The real question is whether we, as a species, will sustain the effort long enough. Whether the work will continue across the shifting political cycles and the changing priorities and the slow turning of the generations that such a project would require. Whether the dream of reaching the nearest star, the dream that has lived in serious thought for 60 years now, will remain compelling enough to drive the long, patient work. And that is not a question of physics at all. It is a question about us, about what we choose to value and to pursue across the span of centuries. And it may, in the end, be the harder question of the two. There is something worth wondering about, gently, as the night grows late. What is it about this particular distance that keeps drawing thoughtful people back to it, again and again? Part of it, surely, is the planet, that confirmed world in the habitable zone, a real object with real implications that pull the imagination forward. Part of it is the makeup of the system, two sun-like stars and a red dwarf, offering two separate avenues of hope in a single destination. And part of it is the distance itself, which is, paradoxically, just close enough to make the dream feel possible. 4¼ light years is near enough that the travel time, though long, does not stretch into the truly unimaginable. Near enough that the delays in communication, though great, are not measured in centuries. Near enough that the numbers, though vast, are not entirely beyond the reach of careful thought to address, at least in principle. The very nearness that makes Alpha Centauri so frustrating, by showing us how far short our tools fall, is also exactly what makes it a target worth dreaming of at all. If the nearest star were 10,000 light-years away, there would be no community of dreamers working on the problem. The goal would be so plainly out of reach that no one would bother. But 4¼ light-years is just close enough to keep the dream alive, just close enough that every generation of physicists and engineers looks at the problem and concludes, not yet, but closer than before. That gentle tension between the achievable and the impossibly difficult is precisely what makes Alpha Centauri the quiet center of all our thinking about the stars. It is the simplest possible version of the interstellar challenge, the nearest case, the minimum test. If we cannot reach this, then we cannot reach any of it. And if we can, then everything that lies beyond becomes, suddenly, conceivable. There is one last perspective worth holding before we let this long night fade towards sleep, and it is the view from the other direction. Imagine standing on that distant world circling Proxima and turning your gaze back toward home. Our sun from there would be a modestly bright star, not especially remarkable, sitting in a different constellation than any we know. For the patterns of the star rearrange themselves when seen from a different place. And our entire solar system, all the planets that loom so large in our own imagination, would be invisible, lost utterly in the glare of that distant point of light. The Earth itself could not be seen at all. Nothing we have ever built would be detectable. From 4 light-years away, our whole world, with all its history and all its striving, would be nothing more than a faint companion to an ordinary star, indistinguishable from any other. And yet our voices have already crossed that gulf. The faint radio glow of our civilization has already washed over that distant world and continued on. The light of our existence arrived there long ago, while we ourselves remain here, still working out how we might one day follow. That, in the end, is the gentle shape of where we stand. We have sent our signals ahead, and we wait, still on a single world, dreaming of a crossing we have not yet learned to make. There is, perhaps, one final and stranger possibility to hold lightly as you drift toward rest. It is the possibility that the distance itself is the answer to the great silence. That the universe is simply built at a scale that makes it almost impossible for life in one place to reach out and touch life in another. That every civilization that has ever arisen wherever it arose looked up at its own night sky and saw the same thing we see, an immense and patient wall, resistant to every tool. That the silence we hear when we listen is not the silence of an empty cosmos at all, but the silence of a universe full of life, each spark of it isolated upon its own small world. Each one gazing out and wondering, each one unable to cross the gap to its nearest neighbor. We do not know that this is true. We hope quietly that it is not, but we should be honest enough to admit that we do not know. And so we end where we began, with a single point of light in the southern sky and a single small number, 4¼ light years. It does not look like much written down. 4 of anything is not very much at all. But behind that gentle number lies an ocean of space with no bottom to it. 40 trillion kilometers of vacuum and cold and radiation and silence. Where nothing human has ever been, and where nothing human will arrive in any future we can foresee, using what we now know how to build. Behind that number sits a small red star that will still be quietly burning long after our own sun has swallowed the inner worlds, and faded into darkness. Behind it sits a world that might hold gentle pools of water, or might be a scorched and airless rock, blasted by radiation again and again, and we cannot yet tell the difference from here. Behind it sits the oldest and deepest question we have ever asked, still alive and still unanswered. Are we alone? And behind that question sits the quiet, uncomfortable, and yet somehow peaceful possibility that the distance itself, not our cleverness, not our resources, not our will, but the sheer physical scale of space, might be the answer all along. But we are not at the end of this story. We are very near its beginning. Every paper written about fusion, every small sail tested in orbit, every telescope turned patiently toward that distant world, every calculation of a mission that may never fly, every hour spent imagining how a ship might tend itself across the years, all of it is the earliest page of a chapter whose ending we cannot yet read. The distance to Alpha Centauri is, right now, the hardest distance there is, not because it is the largest, for it is not, but because it is just barely out of reach, just far enough to defeat everything we have built so far, and just close enough to keep us trying, generation after generation, looking up at that single bright point in the southern sky and wondering what waits beneath its dim red light. So the next time you find yourself beneath a clear dark sky, and your eye falls upon that brilliant point of light low in the south, the one that looks single to the eye but holds 3 suns within it, remember what it is. It is the edge, the place where everything we have done so far comes quietly to an end, and everything we might one day do begins. It is the nearest star, the farthest place we have not been. And somewhere within it, a world the size of our own turns slowly, completing its short year every 11 days, bathed in the perpetual half-light of a tidally locked sky. Beneath a star too faint to see from here without aid. We do not know what waits upon that world. We may not know for a very long time, but we know that it is there, and we know the distance, 4¼ light years. The most frustrating number in all of science, and perhaps the most patient and beautiful invitation the universe has ever offered us. For now, though, there is nothing more for you to do. The stars will keep their distances, as they always have. The questions will still be waiting in the morning, no nearer and no farther than they are tonight. You have traveled a very long way in your imagination, all the way to the nearest star and back again, and you have arrived safely here, exactly where you began, warm and still and at rest. Let the great dark ocean of space drift quietly behind your closing eyes. Let the small red star burn gently somewhere far away, asking nothing of you at all. There is no gap for you to cross tonight. There is only this quiet and this stillness and the slow, soft rhythm of your own breathing, carrying you gently down toward sleep. Rest now. The universe will keep its secrets a little longer. And it will still be there, patient and vast and full of wonder, whenever you are ready to look up again. Good night.